Akinaka from University of Tokyo. I'm a little afraid that I put a scary title here. So revisiting Clean-Slate approach to redesigning the internet. So well, I don't intend to upset anybody, so I just question to myself. So let me give this talk. So first I want to give you an update of what we have been doing. So I'm leading the vNode project in Japan, and at the bottom line, you can think of this as the Japanese version of GEC14. And we have been running this project. We ran a first round from 2008 to 2010, and that was collaboration research among these 6 institutions. And now we add one more institution to KDDI, which is the second biggest carrier in Japan. And we're going to go for another 3 years from now and doing a mini Genie sort of project. So the vNode infrastructure is now deployed in Japan, and we have 7 vNodes and 2 network connectors. Network connector is connecting external network into a slice that we create on top of a vNode. And 11 access gateways, we can connect to these slices from the internet. And our goal is to achieve deep programmability for experimenting with arbitrary protocol, not necessarily an internet protocol. So now, a Slice Around the World project is going on, and the next talk, Joe is going to talk about it, I think. And we are trying to ship one vNode onto MLab, Protogeny lab at the University of Utah, and we worked on that, and shipment is delayed, unfortunately, but we can do that in 1 week, I hope. Okay, so now it's extended to the US. So what we have been doing is that we wanted to enable deep programmability for backbone network. So we have a giant rack of machines connected via GRE tunnel, so we can run arbitrary protocol between them. And what we have done is that we can create slices for running arbitrary protocols and a programmability for both control plane and a data plane. And this is mainly focused on wired and fixed network virtualization. Okay. And now what we are doing is deep programmability for network edge. And we wanted to have some tangible small form factor one new version of vNode, which is deeply programmable as well, even at a layer 2 protocol, yet high performance. And we wanted to do fixed mobile converged slicing. So if you look at this picture, this edge network includes wireless AP, so we wanted to slice even the wireless AP. So taking these challenges, we worked on something called Flare. So I gave a demo yesterday, and lots of people came. Thanks for that. And it's an open, deeply programmable switch. So we want to resolve all these challenges that we listed. So the Flare architecture looks like this. So this is the logical view of our Flare switch, which is very different from OpenFlow switch that you know very well. So at the very bottom, we have a hardware. It's a combination of a general purpose processor and a many core network processor. And you can create a software layer on top of that, slice 1 through a number of slices, like slice 1, 2, slice n. And on each slice, we have a data plane and the control plane so that you can inject the arbitrary programs in there. And usually a switch has physical ports, and we give each slice the same number of virtual ports as physical ports. So, and in a sense, we are giving each slice an illusion that it owns entire hardware, but it's actually virtualized. So slice 1, thinks that it's owning, entire hardware switch. And we worked on, we developed something called a node manager and a packet slicer. So when a packet comes into these physical ports, so it gets classified into one of these slices and then gets switched by arbitrary software that we inject. So by using this Flare switch and also Flare access points, so we wanted to slice the edge network into, like in this picture. So we take the wired switch network and connect all these edge devices like Android, laptops, and to Flare AP and Flare switches. So we developed a version called SolarWind, and in this picture, I depict the architecture of virtualization we do in Flare switch. We have a Flare controller at the top, and we talk to node manager in each switch, and we have several boxes here, and each box represents a sliver, and a node manager can create, remove, and let you access these slivers, and the sliver consists of two parts, C plane and D plane. So if you notice, only D plane has virtual ports, again, the same number of virtual ports as the physical network interfaces, and then you can inject programs in this, developer programs into this C plane and the D plane. Well, I like a Keynote animation, so I switch from PowerPoint to Keynote. Okay, so now I'm going to explain how this switch works. When a packet comes into port 1 of the physical network interface, okay, it goes to the place called slicer slice, and the slicer figures out in which slice that this packet belongs to. So it turns out that this packet it belongs to slice 1, so it gets sent to slice 1 and stripped off is the slice ID, and then packet goes to a D plane of slice 1. An interesting switch happens here, and it gets to the port 4 of the virtual NIC. Then it gets shipped to number 4 of the physical interface. Okay. So then the other packet comes in, goes to slicer, and this time we figure that it belongs to slice 2. It gets shipped to that slice 2, and then it goes into D plane from the port number 1. And an interesting switch happens, and then this time we are sending this packet from number 3 of the virtual port. So then it goes to the physical port number 3 and gets sent to other places. Okay. So D plane can be actually shared, and from multiple other slices, slice 1 and slice N and slice K are now sharing the data plane of the slice K. So you can do this kind of thing in a Flare switch. Okay. So now I explain how we classify packet into a corresponding slice. So we developed 2 versions. Now the generic slicing, it's called a DarkFlow version, and we can take arbitrary offset and arbitrary length and multiple parts and figure out what kind of slice ID that we can put internally at the head of the packet. And a trailer slicing, it's called a SolarWind version. So we explicitly attach slice ID at the end of the packet. And then what we do in a slicer slice is that extract this slice ID from the trailer of this packet. So it's called a trailer slicing. So by doing this, packet trailer slicing, so we can achieve very lightweight network virtualization. In a sense, you can view this as a lightweight tunneling protocol. So we embed a globally unique slice ID at the end of the packets. So then you can have the isolated network namespace in the head of the packets. Okay, you can differentiate these packets, isolate these packets per slices. In the DarkFlow version, we have a slicer API. So we can do slicing using the header matching, trailer matching, and the flow hash, and the regular expression matching if you want to do that. But so this version, we are still working on that, so I don't have a demo for this one. And I want to explain, we define the 3 primitives in the Flare switch. So the first one is called slicer, which extracts the slice ID from the packet. And the second one is called the Redirector. So we are Demux, max, to and from slices. And programmer, finally. So we execute programs on slices. Okay. So this is the same story, but I explain in a different view. So the packet comes in. So the first, the slicer extracts slice IDs. So packet comes into the from the physical port. So then a slicer figures out which slice ID this packet belongs to. So we attach this slice ID at the head of the packet, and we do internal classification, and then we Redirector doing the Demux and the slice ID. It gets sent to a corresponding slice, and then we strip off the slice ID. So the programmer comes into play now and do some packet processing and do some classification, and it gets shipped to the physical port again. So this is how our flare switch works. The SolarWind version, the implementation, is a we use a hybrid of many core processors and x86 processors. It's a one new form factor, so you can play with it in your lab. And we do trailer slicing, and we embed a slice ID in the packet trailer. We have 4 ports for 10 gigabit port, and we can do a non-blocking. We can support up to 2 data plane slices if you want to do non-blocking switching. So it's very, very high speed. And we can develop up to 5 data plane slices due to the hardware limitation right now, but we expect that this number will be much higher. And control plane and the data plane, so this is the good part of this switch. We have a Linux programmability. You can develop using a click, for example. So if your students, as long as your students know how to program Linux, so then you can develop your own switch. And right now we are enabling OpenFlow software in one of these data plane and running a controller in a controller plane. So using this switch, what we could do is that we can run multiple protocols at the same time or multiple controls at the same time. So by looking at this picture, slice 1 is running an Ethernet switch. The slice 2 is running a new layer 2 switch, which I'm going to explain later. And an OpenFlow switch is running the slice N. It's just a matter of how you classify packets into individual planes. So this is the difference chart between OpenFlow and the flared switch. And we can support arbitrary frame, and we can handle non-internet protocol, for example. And a control plane, we can define multiple APIs, including OpenFlow compatible ones. And a data plane, for example, packet processing or new protocol handling, we can do that within the switch. And also, a programming model is very different from OpenFlow. OpenFlow does a flow pattern match and action. So the flare, we have a Linux container. So then we can run a multi-threaded click. And a processing environment, the processing environment is integrated in our switch. And in the DarkFlow version of flare switch, we fully support a slicing programmability. So the disclaimer here is that we are not competing with OpenFlow technologies. People ask what's the difference between the OpenFlow and the flare switch, so I just give this different chart. So now the question is that, okay, we have deep programmability in this switch. How deep programmability that do we want? So several questions here to ask. So some people say control plane programmability is good enough. Why don't we have a data plane programmability? We don't. So, but some people say, I want to do caching, transcoding, DPI within the switch. And so I question, I give this question to myself, and we pursuing a clean slate design, redesign of the internet. For example, can we change the layer 2 protocol using your switch? Okay. So I want to give this example to you. So a case in a data center network. So some people complaining that we have limitation in the MAC address space or VLAN ID space because it has only 48 bits and 12 bits respectively. So sometimes conflict happens when you migrate VMs from one place to another, and also the number of tenants are increasing in the IaaS environment. So we want to have more bits in this space. Right? Some people argue that you can extend a MAC address from a current 6 bytes to 8 bytes, or we can develop VXLAN type of technology using a UDP tunnel. But we ask this question to ourselves, why not just extend a MAC ID space through deeper programmability enabled by flare switch? Okay. So we just extend that to double the space of the MAC address. We are running a 96-bit MAC address using Flare switch, and the slice 1 is now implementing 96-bit MAC extended MAC switching using CLEC software. And in this picture shows slice 1 is handling this extended MAC, and also end system 1 and end system 2 are also handling this extended MAC address. And people ask, what the performance is like. So the performance is very good. So we can achieve 10 gigabit switching for a 2-port. And this is a TCP testing. So MTU size is 1500. And if you use 4 cores, we can achieve 10 gigabit, close to 10 gigabit. So it's very high speed. And we can even try VM migration with extended MAC. Well, I forgot to mention that we are just changing the layer 2 protocol, so we don't touch any IP protocol. So you can run existing software like Apache. It's totally transparent to your applications. And this is a TCP dump that I'm running. It's a recorded video. So if you notice, our TCP dump is showing that the MAC address is not 6 bytes. It's 12 bytes. It's a funny looking TCP dump, but it's real. And we worked on the ARP protocol and everything. And also the Flare controller. Sorry, I'm rushing because I'm running out of time. So the Flare controller, you can create a slice. Going to this web portal, you can create a slice, and assigning a slice to a switch. For example, I create SolarWind GEC14, and you can list up the slices that you created, and then you can SSH into C plane of this slice, and then to SSH again to D plane. Okay. Now we are logging into the D plane, and there's a sample.click. We can run a click there, and this is a multi-threaded clicks. So we are running the 5 threads in this click and doing this extended MAC switching. Okay, this can be done very easily, and my postdoc developed this software in 1 week. And we can run 2 different kinds of switching using a trailer slicing. We attach a slice ID at the end of the packets, and slice 1 is running extended MAC, and slice 2 is running normal Ethernet switching. And also we run the same thing in end system 1 and end system 2. So these 2 protocols don't collide each other because we isolate them using the slice IDs. And also, the network namespace full virtualization is possible. So in this example, we are running Ethernet switching, totally independent Ethernet switching, implemented in the slice 1 and the slice 2. So for example, you can put exactly the same MAC address, exactly the same IP address, run at the same time, sharing the same wire, the same equipment, but they don't interfere with each other. And the beauty of this trailer slicing is that we can insert any existing network equipment between end system and this switch, because existing switch only looks at the header of the packet, so never looks at the trailer of the packet. So you can scale up the number of end systems connected to this Flare switch. Okay, I have only 1 and 20 seconds. So one more thing. So I take the same idea and try to implement that in a wireless slicing in a wireless LAN access point. We call it a Flare wireless LAN access points. So in the same design, so the access point has usually 2 ports, a wireless port and a wired port. So I give each slice 2 ports here, wireless and wired, which is connected to via classifier and a slicer. And Android phone, we also hack the Android phone kernel so that we can attach a slice ID at the end of the packets. So yellow slice 1 is emitting the packets with a yellow slice ID, and the red slice number 2, Androids are emitting the packets with the red slice ID here. And then the packets goes to the yellow or green, yellow or red correspondingly. Okay. So what we could do is that we could do very interesting thing. Like we can assign slice per device. Okay. Each Android has its own slice. Or if we virtualize Android operating system, so then a physical phone has a multiple virtual operating system there, and we can assign slice ID for each virtualized operating system. And also we can do slice per application. We have done only the first one, slice per device. So we developed something called a slice selector. And we bring up this application and say, okay, I want this Android phone to be in a red slice which runs IPv4 protocol. Or if you tell this Android that become an IPv6 device so that it runs on this red slice. Okay, I know that I have only 45 seconds, but I'm showing this video at last. This is the video that I took. So this Android phone, you bring up this. Okay, so first it starts with the IPv4 device because it belongs to the IPv4 slice. Okay. And if you check the IP address of this phone, going to check my v6.com, which shows you IP address. And now we are changing the Android phone's slice to IPv6 slice. So then now it became a IPv6 device. So now go to the same website to check what's the IP address of this phone. So this website is very interesting. If it's accessed from a v6 device, it shows the v6 address. If it is accessed from the v4 device, then it shows the v4 address. Okay, now it's showing the v6 address. Now we change back to IPv4 slice, and now it takes some time, but now it's changed to IPv4 slice. And if you refresh this web page, so then it's going to show you IPv4 address. Okay. By doing this, you can turn a slice that this Android phone belongs to very easily because of the very lightweight of the virtualization that we do. So this is my last slide. Oh, actually, I have two slides. So the conclusion. So we might recall what we initially aimed at, namely, we were saying clean slate redesign of the internet, but I'm asking myself, can we just change the layer 2 protocol, for example, if we say, we clean slate redesign? And also, vNode and Flare projects are now, turning into a second stage, and now put forth edge area network virtualization. And we try to achieve deep programmability. So I can't do this by myself. There are lots of people involved. So this is a credit role. And at the end, I thank GPO, especially Chip, for discussion and giving us opportunity to present our work. Thank you very much.